and this is what I'm going to do. So, my problem. The problem is this. Is there a secure routing algorithm? And I have to be more specific, because now I have a model and I know exactly what I want. What I mean by this is there a routing algorithm that will deliver immediately, or almost immediately, the packet to the destination, provided, of course, that there is a path from the source to the destination which has no faults, no faulty nodes. Because if every path is occupied by the enemy, then there is no hope in hell of ever getting to the destination. And the immediate delivery has to do with the following. I don't want my routing algorithm to keep on trying. So it tries to find a path, it fails. Then it tries another one, it fails. That is not secure. There are applications in which you need to know the packet has to go immediately. If it doesn't go immediately, you may get all sorts of problems. The applications I have in mind, say, for example, are critical infrastructure applications. So they may be a nuclear power station, something may go wrong, the message has to go out. If you stop it for 10 seconds, then you've had a disaster. So the answer is, of course, flooding works. Flooding will sort of seep through. If there is a nice path, it will find it. That's what flooding does. However, flooding is too costly. Flooding could trigger a denial of service attack if the network is very dense. So that's not enough. So let me reword my question. Is there a secure routing algorithm which uses as route a path and not the whole network? And the answer is no. There isn't. Why? And I will give you a very simple proof. It's nothing to do with this by waving my hands. So the question is there a reliable way of deciding a priori whether a node is faulty or not? And in my threat model, the adversary was allowed to choose at the beginning of the system, lifetime system, a set of malicious nodes. Now, there is no reason why the adversary will tell me which ones the adversary has chosen. That's part of the game. I mean, the nodes that are malicious are hidden, they are there, and they will only maybe later on be revealed. If there is any scheme of being able to discover what the adversary chose before the nodes exhibited or sort of did something wrong, then you would be able to guess what the adversary has done. So if there is such an algorithm which can find a path which has no faulty nodes, then you can use that same algorithm as a trigger to discover what the adversary, which set the adversary chose before the nodes exhibited did anything wrong. So you cannot a priori decide whether a node is malicious or not. You have to wait for the node to misbehave. So I will try to find two solutions to this problem. They are approximations. They converge to what I want. And the first one uses a reactive approach. The second one uses a proactive approach. The reactive approach is you capture the bad guys. You find the bad guys. If you find the faulty nodes, then eliminating the one at a time, what will happen, since the adversary can only choose a certain number, eventually the adversary will lose because he will lose all his sort of nodes, and then the system will run perfectly because you won't have a malicious set, at least in this approach. The other one tolerates malicious behavior. It tolerates at some cost, and I will describe how it works. Before I do it, I want to quickly point out some of the problems one has when one tries to trace malicious behavior. So malicious behavior will be traced as follows. Nodes, good nodes, non-malicious nodes, will observe malicious behavior. What they will do is then sign a report, which report will say that node A signs below that node B is malicious, and the signature by node A. You get this. The question is, who is the faulty node, A or B? it could be that A is truthful in the statement and that B is malicious, or it could be that A is a liar. You can't say which one. So what you do is you throw away both. That's one approach. The other one is when you try to trace malicious behavior, one way is to actually look at failure reports. If things happen, if certain paths are more vulnerable to failures, then it may be more likely that there is a malicious node on these. That argument is good in some respects, but it can't be supported, because what will happen is all these rates, which are based on reports, can be affected by malicious nodes lying and giving faulty reports or no reports at all. So I will focus on k-adversary sets. This is the Byzantine thread sets. And the way I view the security is as follows. If I'm using tracing, then what you do is once you trace, you throw them away. Each time the number of bad nodes is lowered. Eventually you win that way. Another way would be to get more than k nodes, if you know what the threshold is, to countersign. So you would want a certificate by k plus 1 nodes to say that one node is bad. If you know that k is the maximum, then that's how you can get away with it. I'm not going to describe. I have two protocols here which are very nice. I'm not going to describe them. You can find them. I think I will post on the web page the paper.
So I have a question. Did you change the question with the immediate delivery? Because your approach is going to guarantee immediate delivery, right?
Not here. The other one, the multipath. So this one doesn't address immediate delivery. What it does is it says the following. It does address in the following. So let me point. So what happens is this. So I does address it, and I'll come to it. But thanks for pointing it out. Give me a minute. So this is called optimistic, and it's called optimistic because if there is no misbehavior, if no node misbehaves, then the cost is exactly the same as any of the other protocols. You don't pay any more. So this is why it's optimistic. In the honest case, with no faults, there is no extra cost. If there is misbehavior, there is extra cost to trace the misbehavior. And I'm just keeping them. The theorem will say the following. It says that, and it's provable. It's provable in the model I just described, the models I just described, that one of two things will occur. Either the packet will be delivered immediately to the destination, or if that doesn't happen, you will trace a faulty node. So you have one of two. Okay? So the protocol somehow in a clever way, so the packet goes from source to destination, and nodes don't do anything more than what they normally would do. But if something goes wrong, then there is a second. So it's a two-pass. Forward, downstream to the destination, upstream back to the source. Downstream goes the packet, upstream comes the acknowledgement. That's what you always need. Now, if there's misbehavior, the nodes use a special sort of the way it works is you have so I'll go back here. You have each node has a timer, and you count on the time it will take for a reply to come back. Something should come back. If something does not come back, something has happened. The nodes are instructed to always send back reports, negative reports. It's like nodes committing suicide, because such a negative report automatically has the effect by that the signer of the report and the reported failure node, they will be deleted from the system. So they are both, yeah?
I have a question about the use of the negative acknowledgements. It seems to me like very difficult to prove that you did not receive a packet.
Oh, right. So that comes in the proof. What happens is that all these timers are set in such a way so that if failure occurs, the